Hello everyone, welcome to AB Chemistry. In this video you are into chemical kinetics, the very fundamentals. When we begin studying chemical kinetics, the very first and fundamental question that we have is that why chemical kinetics? Why kinetics? This is the fundamental question that we have. Especially when we study thermodynamics, we already know that which processes are going to happen spontaneously, because thermodynamics tells us that which are the processes that are going to happen spontaneously. So we know that which are the chemical processes that is going to happen and which are the processes that are not going to happen. So we already know an important thing from thermodynamics. So what is the need of studying kinetics? For that answer, what I say is that when we study kinetics actually gives us that out of all these spontaneous processes, which are the processes that are relevant to us in our time scale, in our life scale. That means which are the processes that are biologically happens within a biological time scale. Okay, to understand this, we can think about the phenomena between graphite and diamond. Graphite and diamond. Both of them are forms of carbon, right? Graphite and diamond, both of them are forms of carbon. And if you think thermodynamically, then what you see is that experimentally we can see that graphite is more stable thermodynamically compared to diamond. Okay, so if you study thermodynamics will tell you that if you have a diamond should spontaneously or readily get converted to graphite. However, we have seen that none of our diamond jewelry ever getting converted to graphite in our lifetime. Okay, so this is very, very important. In how much of time we are going to see a spontaneous process happening is not dealt with by thermodynamics. That has to be dealt with by kinetics. Why diamond to graphite? This particular, although it is a spontaneous process, why it does not happen in a very short period of time, or at least in a lifetime? Because the process of diamond to graphite, although diamond lies, if we plot energy here, then diamond and graphite, we can see that here lies graphite and here lies diamond. So energetically diamond is less stable compared to graphite, but the conversion from diamond to graphite has a very high barrier, which is not easily surmountable. Therefore, this process, although thermodynamically spontaneous, is never going to happen within a lifetime. So although this is a thermodynamically spontaneous process from diamond to graphite, but this is not a relevant process to us as human beings on Earth. So this is dealt with, this kind of thing is dealt with by kinetics. Another example that we can take is the example of skin and soap. Thermodynamically, skin should get dissolved in soap solution. It should get dissolved if we talk about thermodynamics. However, this process is a slow process. dissolving of skin and a soap solution is a slow process, and therefore even if we take regular bath and soap, still we never see that our skin getting dissolved in the soap solution. It is a slow process, and therefore we can safely take baths regularly with soap. So all these are simple examples, and there are more complicated chemical reactions that we have to deal with, and in that case, which processes are relevant to us and a time scale of our importance, that is going to be decided by the kinetics, the rate of that process. By kinetics, what we mean is that basically we deal with the rate of a process, how fast something happens or how slow something happens. Okay, which processes are going to be relevant to us in our lifetime and which are not. Okay, so before going into the actual kinetics, we have to know a few fundamental concepts that is important while studying kinetics. One of them is stoichiometry. So if we represent a simple reaction like this, that A plus B plus dot 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 dot. These are the reactants, and these reactants react to form some products which we represent by small y of y plus small z of z plus dot 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 dot, like this. So where this A and B, capital A and capital B, are reactants, this is how we represent chemical reactions. This is called the chemical equation. And Y, capital Y and capital Z are the products. And these small y and small z are the corresponding stoichiometric coefficients. So small y is the stoichiometric coefficient for y, and small z is the stoichiometric coefficient for z, product z. And when we talk about reactants, this has to be, you have to be very careful. When we talk about reactants, the stoichiometric coefficient of A is not simply A, it is minus of small a. Okay, and the stoichiometric coefficient of B, reactant B, is minus small b. Okay, so this we have to be careful about. And these stoichiometric coefficients are important to know. This takes some important role while we are studying the rates of a reaction, or while we are studying the overall kinetics of a reaction. Okay, so stoichiometry can be of two types. Okay, it can be time dependent stoichiometry, or it can be time independent stoichiometry. Time dependent stoichiometry are those reactions which the stoichiometric for which the stoichiometric coefficients are not constant throughout time. We say that those reactions follow time dependent stoichiometry. And for those reactions where the stoichiometric coefficients are always constant throughout the reaction, in that case we call that as time independent stoichiometry. Okay, so let us take two examples. When we are talking about time independent stoichiometry, this is the simpler one. It is the stoichiometric coefficients are always constant. So we can write a reaction like this: hydrogen molecule reacts with bromine molecule to form two molecules of HBr. Okay, so this stoichiometric coefficients, which is -1 for hydrogen and -1 for bromine and 2 for HBr, all these stoichiometric coefficients are constant throughout the reaction. Okay, let us take another example where acetone, which we represent is like this. Acetone decomposes to form methane, ethene, and carbon monoxide. If you balance, what you will see that there will be two acetone molecules forming two methane, one ethene, and two carbon monoxide. Okay, but what you will see from this, you should it appears, it seems that if X amount of acetone is consumed, then X amount of methane should be formed, and X by 2, that means 2 moles of acetone reacts to form and decomposes to form 2 methane molecules, right? So if X amount of acetone is consumed, then X amount of methane should form, and X by 2 amount of ethene should form, because 2 moles of acetone leads to only 1 mole of ethene, right? So if X amount is consumed, then X by 2 amount of ethene should form. Similarly, X amount of carbon monoxide should also form. But throughout the reaction, experimentally what we have seen is that throughout the reaction, this is not true. This is not true. What actually happens is that this reaction does not happen in one step. Okay, there is a formation of intermediate in this reaction, which is thermodynamically, it has a thermodynamic stability. This intermediate has a thermodynamic stability. Therefore, when this acetone decomposes to form the intermediate first and going to methane and ethene and carbon monoxide, this intermediate actually is populated significantly. So that X amount of acetone, when it decomposes, it does not straight away form X amount of methane. Some amount significantly populates the intermediate, and only a fraction of that goes to methane very fast. Okay, so if you determine the amount what is consumed for acetone, and if you determine the amount in the same time, if you determine the amount that is being formed for form of methane, you are not going to get the same value. Although stoichiometrically you should get it, but you are not going to get it because there is a significant population of the intermediate. So this kind of reaction, which actually do not follow the stoichiometry throughout the reaction, are called following the time dependent stoichiometry. Okay, these are more complicated to study, but if a reaction follows time independent stoichiometry, then there is some simplicity to deal with it. Okay, because then the rate of consumption and rate of formation, the rate of consumption of the reactants and the rate of formation of the products have some relationship, have some simple relationship that we are going to see now. Let us consider for that let us consider that a simple symbolic reaction where a reactant A reacts with 3 moles of B to form 2 moles of product Z. Okay, and this is a time independent stoichiometry. Okay, so all the time when 1 mole, the stoichiometric coefficients we know that -1, -3 and 2, right? So all the time if X amount of A is consumed, then at the same time for B it will not be X amount, then the amount that is consumed for B will be 3X, because for one mole of A there will be 3 moles of B reacting, right? So for X amount of A there will be 3X amount of B that will be reacting, and it will form 2X amount of Z. So the rate of consumption of A is not equal to the rate of consumption of B, and again in turn is not equal to the rate of formation of Z, right? So basically how we represent the rate of consumption of A mathematically, it is simply the change of concentration of A with respect to time. When we change time, in that duration of time how much of A is consumed, that is the rate of consumption, right? And that is mathematically we can represent it as dA consumption. Therefore this is the minus, so it will decrease. Concentration of A will decrease with time. It's a reactant, it will be consumed. So rate of consumption we can represent like this, where this is square bracket A represents the concentration of A. It is the concentration of A. Okay, and this whole term is the rate of consumption of A. Rate of consumption of A. Similarly, minus D concentration of B dt represents the rate of consumption of B, and dZ concentration of Z dt represents the rate of formation of product Z. Okay, and from the earlier discussion we have seen that minus dA dt is not equal to minus dB dt, which is again not equal to ddt of concentration of Z. All these rates are not equal. Okay, but from simple logic we can understand that when X amount of A is being consumed, then 3X amount of B is being consumed. That means the consumption rate of B is 3 times faster than A. And why 3 times? Because its stoichiometric coefficient is minus 3, and the stoichiometric coefficient of A is minus 1. So stoichiometric coefficient of B is 3 times the stoichiometric coefficient of A, right? And similarly, the rate of consumption of A is not equal to rate of formation of Z. While X amount of A is being consumed, then 2X amount of Z is being formed. That means the rate of formation of Z, the product Z, is 2 times faster than A. Why 2 times? Again, because the stoichiometric coefficient, the absolute value of stoichiometric coefficient of Z is 2 times the absolute value of stoichiometric coefficient of A, right? So basically the rate of consumption and rate of formation for time independent stoichiometry reaction follows a simple formula. Okay, it has a simple relationship. We can say that 1 by nu A ddt of concentration of A is equal to 1 by nu B ddt of concentration of B is equal to 1 by nu Z ddt of concentration of Z. Okay, this is the simple relation where nu A, nu B and nu Z are the stoichiometric coefficient of A, B and Z respectively. That means for this specific example of reaction, nu A, instead of nu A we have to put -1, instead of nu B we have to put -3, and nu Z we have to put 2. Okay, if we put these three values, the stoichiometric coefficient corresponding, we are going to see that these expressions are going to follow this specific relation. Okay, so this is why stoichiometry play an important role while we are studying chemical kinetics, where we are going to the rates of consumption or rates of formation. The stoichiometry actually plays an important role. Therefore, before going into studying the actual kinetics or actual rates of a reaction, we need to understand the fundamentals of stoichiometry. So this is the part 1 of fundamentals of chemical kinetics. We will continue in the part 2. So see you in that video. Thank you.